Hello, everybody. Happy Friday, and welcome to today's webinar on turbochargers. I am Amanda Harmoning. I am an admin assistant here at AERA, and I will be helping moderate today's event with my colleague, Rob Monroe.
Hey everyone, yeah, Rob Monroe here. I look after membership and technical development over at AERA, and Amanda and we're going to be in the background today to help answer any questions that you may have throughout the webinar. We're going to leave lots of time at the end of each webinar for Jay to answer those questions you may have. And just a reminder, today's webinar is a two-part series. So we're going to have part one on turbocharger theory. We'll take a 5-minute break, kind of get you to be able to stretch your legs a little bit, grab a drink or whatever, and then we'll jump into part two on failure analysis. So we do have an announcement. AERA has just hired Fernando Corello, and Fernando is going to be our Spanish-speaking tech specialist. And we're looking forward. He's going to be a huge asset to us here in the tech department to help some of our international members out. Fernando is from Argentina. He speaks several languages, including Spanish, of course. And Fernando spent many years in valve train engineering, and he's going to be, he was at Basso Valves for years. So looking forward to have Fernando on board. There is his email address. It's fernando@aera.org if you want to reach him directly. And again, huge asset to help us out in the tech department there. For those of you that are on, you've heard me say this before. The tech services department at AERA is your biggest reason for being a member for sure. It's best to, you're making good money on the shop floor doing what you do. Allow us to do what we do best and get you that engine information you're looking for. And that way you can spend your time on the shop floor making good money. So we're there to help you. Another thing, if you want some of the same information at your fingertips that we use when you call us or email us, the Process Pro software, we have 11,000 engines now loaded into Process Pro. And again, when you call us, this is our first go-to on the tech department. This is what we're using to help you with that information. So if you want that at your fingertips, we do have that option for you. It is an upgrade to membership. And again, you can even put your own logo, your own company information right on the printed information that comes out of Process Pro. And you can make it look like it's coming right from your shop. So if you have any questions about that, just put that in the questions box and we can help you out there. Now, enough chit chat from me. Let's bring on Jay Miller of Diesel USA. Now, Jay's got an extensive background in turbocharger systems. This is an honor for us to have this kind of caliber today doing a webinar for us. And Jay's the author of several published industry articles, including he's got a book out there. It's called Turbo, Real World High Performance Turbocharger Systems. So like I mentioned, if you got any questions, I mean, this is the guy to answer them for sure. And if you have that, just put them in the questions box and we'll get them answered at the end. So Jay, how are things going this afternoon?
They're great. Thanks, Rob. I appreciate the invite to be here today.
Yeah, no, for sure. We're glad to have you. I can see your screen. It looks great. You sound great. So I'll just let you carry on. And like I say, any questions for Jay, put those in that questions box and we'll get those over to him. So thanks for coming on today, Jay.
Well, you're very welcome, and I'm very honored to be here. I won't promise that I can answer every question that's asked, but I can do my best. I would like to just introduce myself again. I am Jay Miller. I have spent my entire professional career in the turbocharger aftermarket at various levels, and I consider myself very fortunate to work professionally in an area that I also have very personal high passion about. So that's a real joy, and I feel very thankful about that. I'd like to welcome everybody that's on this webinar, folks from the EU, including UK and Germany, South Africa, Australia, New Zealand, and of course North America. And I also understand there are several students at various schools listening in today. So I just want to welcome everybody, and even those I did not mention by country. Based upon the various aspects of the audience, what I've tried to do in this webinar is gear this thing to have something for everybody. The subject of turbochargers is one that is very popular these days, but there are people who know a very little amount and want to know more. There's some very strong intermediate people Some of what we're going to go through may be very elemental, but we're going to touch on some rather difficult concepts as well. So hopefully there'll be something in here for everyone. So in part one today, we're going to talk about just basically what a turbocharger is and some of the fundamental theories. And then we'll go through turbo anatomy, and I will try to use the proper nomenclature because the nomenclature dynamic is very important. Because as you communicate both with industry peers as well as customers, what you are communicating using the right and consistent terminology will help you to more clearly communicate questions or issues associated with a device such as a turbocharger. And then we'll talk about types of turbochargers. But just before we get into that, I just want to introduce the Diesel USA Group and who we are. We are the nation's largest turbocharger distributor, and we distribute directly from the world's 5 major manufacturers: Garrett, Holset, which is wholly owned by Cummins Engine Company, Borg-Warner, IHI, and Mitsubishi. In addition, we are also a top fuel injection distributor for Bosch, Stanadyne, Delphi, Cummins, Mopar, and a few others. And we are the corporate parent to some allied product lines such as Grizzly, which is a variety of different products, but is most commonly known for EGR, exhaust gas coolers, Avtec brand charge air coolers that some of you might know as an aftercooler, Mass Flow Engineering, high performance diesel componentry, Master Calibrating, and Cardinal Reman. So let's just spend a minute to understand why the popular buzz around turbochargers. This graph represents on a worldwide basis the turbocharger expanding market, where the red line illustrates the growing turbo penetration going from 45% to 61% in just 8 years. And this vertical green line represents where we are approximately today. So as you can see going forward through 2025, the rate of growth is going to continue at the rate that it has been. And that is developing a very, very large potential in the replacement market for turbochargers. So if we look at that same trend by worldwide region, you can see how in North America, there was only in 2017 about 34% original equipment penetration, and is going by 2022 expected to be as high as 50%. By contrast, you look at the European Union in 2022, 76%, but in 17 it was 78%. It's a negative 2%. But the cause of that is basically the fact that in the United States, historically, engine displacement ran on average about twice that of Europe. Europe has been running smaller displacement engines, higher RPM, for many more years, and the turbocharger has been fitted for a longer period of time there. So the real dramatic growth is about a 16% growth rate, compounded annual growth rate for North America. So let's start out with just what is a turbocharger. Very simply, it is a radial inflow turbine that takes the energy from the engine's exhaust that is present in the form of heat and pressure, runs it through that radial inflow turbine before it goes back out the exhaust to drive a shaft. That shaft is connected at the other end to a fresh air compressor, and that fresh air compressor increases the volumetric flow and the air density for the engine to increase the engine's total mass flow and volumetric efficiency. You must remember that pounds of fuel equals horsepower, but you just can't increase fuel flow without the presence of oxygen to burn it. So the increase in airflow, commonly referred to as boost, in and of itself doesn't gain you anything. It's an enabler for the increase in fuel flow rate to burn. So from an operational basics, turbos are a very fascinating device because they're both as simple or as complex as you choose to understand. We're not going to get extremely complex here, but most of your reselling accounts or people that you talk with are not turbo savvy. So I would encourage you to not fear discussions on turbos. Any of you people in business, your reselling accounts need what you have to offer. They need to understand this device. If you retain anywhere close to 100% of discussion of today's webinar, you'll probably end up knowing more than 90% of the people that you encounter in the marketplace. And this being AERA, engine people tend to understand more easily turbochargers simply because they understand the engine dynamics and the turbocharger's role associated with aiding engine performance. So let's start out with turbocharger basics. All turbochargers have what are referred to as 5 major components: the compressor cover, the compressor wheel, the bearing housing, the turbine housing, and the turbine wheel and shaft assembly. Once the turbocharger is assembled and the compressor wheel is mounted onto the turbine wheel, that's commonly referred to as the rotor assembly or the rotor group. So in an operation of a turbocharger, let's talk about it in the 3 machine areas that a turbocharger possesses. It all starts with the turbine because that's where the energy is extracted. So the turbine housing is designed to receive the exhaust gas in these passages, and that exhaust gas flows through the nozzle area here of the turbine as it reaches the tip of the turbine wheel, which is called the turbine wheel inducer. And as that pressure, that high pressure always wants to seek lower pressure. So that higher pressure in the turbine housing seeks the lower pressure this direction and expands against the blades to drive the turbine and create the rotational mechanical energy. Of course, that is then connected to it through a shaft and a bearing system. But there's also an intricate series of heat dams to isolate the high heat found in the turbine to keep it away from the engine's oil that is seen in this area where the bearing system is, and you see a heat shield here that this particular turbo model has to create a dead air space here as a form of insulation barrier, as well as the casting here. But then you also see the cradle of the seal area that is separated and isolating the bearing system where the engine's oil is. So it's all very deliberate design and is very specific in its metallurgical qualities to withstand this environment. The turbine on a turbocharger is perhaps the least understood but the most important in the tuning of a turbocharger to a specific engine's demand rate. And you hear areas, you hear A/R ratios. Some people call it an aspect ratio. I don't like that term. It's incorrect. An aspect ratio is like a 3x5 picture frame. The AR ratio is commonly misunderstood, so I wanted to spend just a couple of minutes here to give you the technical understanding. A is the area at the tongue, and I'll explain what that is in just a moment. The R in the A/R is the radius from the axis of rotation to the centroid or dynamic center, DC, of the volute of the turbocharger. In other words, the RDC. The DC is the point where half the flow passes above and half the flow passes below. So it's the dynamic center, not necessarily the geometric center. So here we have a cutaway of a turbine housing not normally seen that is perpendicular to the axis of rotation. So the area of the tongue is this in square inch or square centimeters area, this being the tongue right here at the first point where the gas is begins to be exposed to the turbine wheel itself. Then these vectors represent the flow and velocity of the incoming gas from the exhaust stream here. And then this represents the radius from the center of rotation to the dynamic center of flow. So the VT is the tangential component of velocity, and the VT at that dynamic center is the mean value of flow velocity. So another way to look at this is the geometric and aerodynamic analysis. What's going on here in the turbine is you have to understand that the engine sees balanced pressure. It wants to see a balance of pressure on the turbine that the pistons are working against during the exhaust stroke, as well as the intake manifold pressure. In a perfect situation, your intake manifold pressure exceeds turbine back pressure. The idea of the turbine housing is to be sized to a given engine's specific flow capacity to give it that sweet spot. And the best analogy is the garden spray hose. Everybody has handheld a garden spray hose. And as you begin to open it, it's got a wide pattern because it's mostly closed. If you open it all the way, it goes out in a stream, but it doesn't go as far as if you begin to close it back a little bit and you get to that optimized sweet spot where you have that farthest spraying stream of water. That's the best analogy to understand what's going on in the tuning of a turbine housing to a particular engine. So in the middle between the turbine and compressor ends, there is a bearing system and support system. And there's a lot going on in here. There are different types of oiling system. This is what's called a separate fed. So the engine oil is ducted into this intake area here. And it's separately fed, meaning that this oil galley right here is going to the thrust bearing area. And then there's individual galleys going to each of two journal bearings in this particular case. These journal bearings are one example where each bearing rotates in relationship to the housing, and the shaft, the turbine shaft itself, rotates in relation to the bearings. Typically, the bearings will rotate at approximately 1/3 of turbine shaft speed, which helps to divide up the speed differential between the relative surfaces. Also, what can be found here are the oil control areas. Many people talk about a turbo's oil seals. Practically speaking, a turbocharger, with the exception of age-old turbos back in the carburetor days, do not have oil seals per se. A turbocharger controls the potential for oil leak by the control of the engine oil. And what's pointed out here in these red arrows is this is the flinger sleeve that is machined into the turbine wheel neck here, where the shaft is usually welded on by electron beam or pulse welding. Then on the compressor end, there's a part called a thrust collar that is either separate or sometimes involved in the same two-function purpose of being an oil flinger that keeps the oil that has come off of the pressurized oil area away from the area of leakage, so that it flings it up into this area, then drains back down into the drain cavity for return to the oil pan. What you see here in this next red arrow is the device that's sometimes called a seal ring, but it's most commonly referred to as a piston ring. And it's referred to a piston ring is suitable because A, it looks like a piston ring, but B, it does the same primary function. The ring seals actually seal, their primary function is sealing the pressurized exhaust gas present in the turbine area from entering into the drain cavity, which that pressure would find its way to the crankcase. There's one that's hidden from view here, but the same thing on the compressor end. that seals the boost pressure from reaching the drain cavity as well. So those seal rings are not oil seals, they're actually gas seals. Then we move to the compressor. And the compressor end is what the engine likes to react to for the increase in fuel flow. And the compressor wheel is comprised of two parts, the compressor wheel, of course, and the compressor cover. The compressor cover has a very important area that has no moving parts and is commonly not talked about, and that is what's called the parallel wall diffuser. And its function is to take the air the highly turbulent air as it exits this radial fresh air compressor and turns it into static pressure in the volute area of the compressor cover before it is then ducted to either the aftercooler or into the intake manifold. So when we put it all together, the cutaway of a turbocharger here, you see how it all basically works. Again, the gas entering the turbine housing expands against the turbine wheel blades and then exits the turbine exducer into the exhaust system. The bearing housing and support in the middle, and the compressor wheel, which the inducer is the center here, and the exducer of the compressor wheels here, the parallel wall diffuser, the volute that gathers the air and ducts it into the engine. It's a fairly simple device to understand, but if you're in the engineering ranks, it's an extremely delicate piece of machinery to design and manufacture. And engineering groups in turbocharger manufacturers are commonly divided up into turbine development people, compressor development people, and bearing development people. They specialize in a general sense in each of those areas to maximize the efficiency, cost effectiveness in the development and the manufacture of the turbocharger. When we get into turbocharger types, the oldest type is what's called a fixed geometry. And the types of turbochargers, going back to the importance of the turbine itself, are really defined by the variation of what's going on the turbine side of the turbocharger. In fixed geometry, you have a turbine housing that has, if you will, a fixed swallowing capacity. And that has worked well on classic low-speed diesel engines, including over-the-highway trucks, where they typically run under 2100 RPM. They'll hit peak torque anywhere from 14 to 1600 RPM. But the lower the speed, sometimes the more valid it is to divide that turbine housing. So inside of fixed geometry, you'll see what's called an open turbine housing or a divided turbine housing. And the divider wall isolates, though the turbine pulses, there's pulse gas energy in the exhaust system, especially in a very high BMEP engine, such as a diesel engine, and isolating that pulse and keeping it from getting diluted such that it reaches the tip of the turbine wheel can raise the efficiency of that turbine to extract that energy, because needless to say, during each exhaust pulse, the amount of energy during each exhaust stroke is greater than the amount of energy present between each exhaust pulse. And so that's what the divider wall in a turbine housing is called. Its proper name is a meridional divider wall. Then you get into waste gates, which is an aptly named device. As its name describes, it sends wasted energy around the turbine itself. It's most easily identified as being typically a smaller frame turbo with an actuator, which is located right here, and an arm that drives a crank elbow that has a flapper valve inside of the turbine. And while it's not exactly easy to see here, what's going on during operation is that smaller turbine on a higher RPM engine, such as a gasoline engine, that that smaller area turbine is driving the boost pressure earlier in the RPM range, but if it's too small, then it would build too much back pressure, and the pistons would see that, and that would increase the engine's pumping losses, and you would get to a point of diminishing return, and your turbine pressure would far exceed your boost pressure. So what happens is that actuator is tuned to turn that crank arm, open up a flapper valve here, and provide in the higher RPMs the ability for that excess gas to be wasted and go out to the exhaust, thereby bypassing the more restrictive turbine housing, so that the engine's upward RPM range is not limited by the back pressure the turbine housing would otherwise create. Then we move into variable geometry. So rather than fixed geometry, we get into VG, or a variable power turbine. There's a number of words that all mean the same thing. What we have in this picture here is basically the variable geometry components with the turbocharger stripped away. And it's more easily seen how the turbine wheel that would be residing inside the turbine housing is surrounded by a series of vanes that will rotate about that blue pin that you see that anchors those vanes, and those open and close, in essence creating a throttle for the exhaust gas as it opens and closes to feed the turbine wheel, so that you have a turbine that acts like multiple sized turbines, and it's tuned to have the proper amount of boost at lower speed and the proper amount of boost at mid-range or at high end, without creating that back pressure that the absence of a wastegate or these vanes would cause. So it's the best of both worlds, and it increases the total efficiency of the turbine throughout a wider RPM range. That's the way most of the world does it. Holset, on the other hand, the Cummins design, the vanes themselves remain in a fixed position, as you see here. And that has theoretically some advantage, because that angle of incidence where the gas passes through the vanes and imparts onto the turbine wheel tip can maintain its optimum angle of incidence for leverage upon the turbine. It's not extremely large, but there is an estimated between 1% to 2% increase in turbine efficiency. And how they then vary the geometry is this plate here moves in and out longitudinally, and that's why the turbine housing is cut out here to receive this vane as it comes in, and then that varies the opening for the nozzle area of the turbine housing to feed, and thus throttles the volumetric flow of exhaust gas entering the turbine. And then the variable geometries today are actuated by either pneumatically controlled devices, which are more and more passé, and today are typically more an REA, or rotating electrical actuator. And this is quite commonly a component that is serviced independent of the turbocharger itself. So it's not uncommon for the turbocharger to be fine, it just needs a new actuator. And that concludes part one.
Excellent,
Rob,
Jay. Yeah, no, really good information. Really good information. So we did have a couple of questions come in, Jay, and what I'll do is, on the first couple of slides that you had, you were showing a cutaway, and you were explaining, there was a cutaway of the bearings. And the question is, what material is used in the bearing on that, like you had there on the cutaway of the turbo?
Probably north of 90% of all bearings, with exception of ball bearings. But the journal bearings are a bronze alloy. There are ball bearings that use ceramic as well as steel ball bearings, very precise devices for rapid spool up. They tend to be more dominant in the performance turbocharger arena than on commercial.
Okay, excellent. Another question, Jay. If turbochargers are used for greater fuel economy, does it make sense to retrofit a turbocharger on a naturally aspirated engine to even get better fuel economy on that?
The short answer is no. If you're going to retrofit a turbocharger, you're typically going to do it for performance reasons. That's a very good question because it's a common misnomer where vehicles and engines are sold with the small turbocharged engines and they have a higher fuel economy. So you take an I4 versus a turbocharged versus a V6 naturally aspirated. The primary gains in fuel economy come from everything associated with it being a smaller engine, less pumping losses, and the accumulated friction of all of the moving parts. The turbocharger is present for one real primary reason, and that is to boost the total horsepower output of that four-cylinder to equal the horsepower output of a naturally aspirated V6. Most enthusiasts will say there's no such thing as too much power. So if you're going to retrofit a turbocharger, to get the benefit of it, you're going to have to increase the fuel flow. You need to change the fuel delivery mapping on the computer so that you maintain the optimum air-fuel ratio. So it's done more for power in a retrofit. It's not wise to retrofit a turbocharger with the objective being an increase in fuel economy.
All right. We're going to go back to that to the bearings again, and this gentleman's asked, what lubricates the bearings since they sit outboard of the oil slingers?
What lubricates the bearings is it's a hydrodynamic bearing system. It's really no different than the engine mains and rod bearings. There's an pressurized oil galley. It's pressurized by the engine's oil that reaches in that cutaway the center of that bearing. Then the oil flows longitudinally out and it drains either towards the middle or the outboard side of that. So the oil flingers are really just managing oil that has left the pressurized cavity. So the bearings are indeed lubricated by pressurized oil.
Okay, all right. And another question for you, Jay. What are those holes you see drilled around the intake on some compressor covers?
Not exclusively, but most commonly that, again, will be seen in performance turbochargers. That is what's known as a ported shroud. The other generic reference is map width enhancement. And what that basically does is if we don't have a picture of a compressor map here, felt that would be getting too deep and involved for the audience perhaps, but every turbocharger has a max and a min flow range. And the minimum is the area of a compressor map known as the surge line. And when a compressor is operating near that surge line, the airflow can become what is referred to as a choppy airflow, and it gets very inefficient. Those holes, also referred to as inducer bleed, allow a small amount of air to recirculate back around from the inlet of the compressor back into the inducer area, and it stabilizes the airflow to make use of a broader flow range of that compressor. And that's especially valuable in a higher or a wider RPM band range engine, such as a gasoline engine versus a narrower band diesel engine.
Okay. All right. Another good question here for you, Jay. Turbochargers that cool with both oil and coolant, how do they work? Which fluid cools which component of the turbocharger?
Typically, in most on-highway applications, water cooling is cooling the bearing housing. there will be a separate water jacket in the bearing housing to cool that component to keep from superheating of the engine's oil in the bearing housing. So just like in an engine, you've got separate water jackets and separate oil galleys and systems. They're isolated. So too in a turbocharger. On certain specific applications, and I'm thinking primarily marine applications, where the Coast Guard law requires that all surfaces be a low enough temperature that you can touch them with your hand, you'll find water-cooled turbine housings. And they look like a landmine because of the series of plugs around the outside of the turbine housing to get the core sand out during original casting. But then that's also where you plumb intake and outlet of water on the turbine housing. But on highway, it'll most always be the bearing housing that is cooled for engine longevity to keep the engine oil from cooking.
All right. Super, Jay. Another question here for you. This gentleman's asked, can you please explain single versus two-phase turbocharging?
Well, that's a very deep concept. I've never heard it called two-phase. I think what the gentleman must be referring to is series turbocharging, and I would liken it to the shop compressor. Your workshop compressor will commonly have a large piston and a smaller piston that achieves a higher pressure in the air system in your shop. So you have the larger piston that compresses at once, and that feeds into the smaller piston that does a second step, separate stage of compression. So in certain engines, and Caterpillar is well known for this, you'll have, it's not a twin turbo, it is a stage or a series turbo setup where you'll have a larger compressor and its outlet will feed the intake of a smaller compressor. So you have two stages of compression. So what the engine sees is instead of 20 pounds of manifold pressure, it might see 40 pounds of manifold pressure. And you can arrive to that pressure ratio while keeping each turbo within its speed limits of what it can withstand. Otherwise, arriving at that level of boost pressure would drive a single turbo to have to achieve a level of speed that it would not have longevity in practical use. And it also provides a greater range or width of airflow than a single turbo's compressor will provide when an engine has to operate over a wider RPM range. Hope that answers the question.
Yeah, no, great answer, Jay. Here's another question for you. What are the net effects of turbocharger application where the system is undersized or oversized for the best choice?
Well, the oversized is the easiest one. So we're probably talking about a retrofit system. And if it's too large, you're going to have severe turbo lag, but there can also be what's known as system lag. And I cover that in the book, where it takes forever for the turbo to spool up, or you're just not building the desired boost level. Turbochargers like to have a power balance across them. And the power balance can most easily be identified through not just a boost gauge, but what people rarely do is to run a turbine inlet pressure probe and then run that to a boost gauge to monitor your turbine and compressor pressures, looking for, at a steady speed of wide open throttle, a balance of pressure, or ideally a higher pressure on the compressor side. In the case of too small or too little, you will build too much back pressure in the turbine and the engine will begin to fall on its nose. It just won't respond above what you would consider mid-range in the upper RPM ranges because you're choking it. It's like trying to run uphill breathing through a straw. It just doesn't work very well. So optimizing the turbo match is the key to tuning one properly to an engine. You can definitely go too big, you can definitely go too small, but you can't go small on the turbine and huge on the compressor unless you have some sort of wastegate or bypass to, in effect, bleed off that excess energy to allow the engine to reach its full potential. I hope that answers the question.
Excellent, Jay. All right, so this gentleman's asked, if we have a crack in the turbine housing, is there a way to repair it, or do we have to replace it?
That's a difficult question to answer, and the reason I say that is there are many cracks that it actually takes kind of a trained eye to realize are a natural state of what to expect, especially in a divider wall. And sometimes those divider walls that they don't have any cooling because they're surrounded on both sides of the volute in a divider wall, and they can crack, but then they are then stress relieved and they won't crack further. Cracking around a turbine housing foot, we'll see in some slides in a moment, can be contributory and evidentiary in a total diagnosis. As a general rule, I know of no legitimate turbo remanufacturer or entity that will take cracked turbine housings and weld them up and call that a fix. There are a few cracks that are benign, but in certain areas or where you see the divider wall cracking too severely in two different directions, that can cause pieces to drop off and fail the turbine wheel and fail the turbocharger itself. It's not advisable to try to repair a turbine housing. And there comes in another consideration there, and that is the turbine housing material. It's doubtful that you would have the welding rod that would be of the proper metallurgical property used in that turbine housing. There's a wide array of different materials used depending on the application, because a turbine housing has to be able to live in the temperature environment, but it also has to be able to contain a burst, which is a very dangerous potential situation.
All right. Yep, sounds good. Jay, on dual turbo applications, how critical is it to have either a single or dual wastegates?
By dual, I'm going to interpret that as meaning a twin turbo setup, where one turbo is not feeding the other. They are both calibrated at roughly half the flow of what the engine demands. So it's a cosmetic looking situation, and I would say that you should wastegate both turbos. There will bound to be a difference of opinion, because that does get into certain choices and perspectives, and I would honor all of them. It's just a choice. If I was going to do a twin turbo, I would want to basically make two separate turbo systems to control that. But they both compressors, of course, feed the same plenum.
This webinar will be split into two parts and get posted out on our YouTube channel. If you want to view this webinar or any other webinars, you can just go out to YouTube and search Engine Builders Association or AERA Engine Builders, and you will find our page. Go ahead, subscribe to it, and check out our content, and make sure you're notified when we post new videos.